Okay, so let's resume from where we left last time. We reached uh, in our last session this type of proof, the constructive existence proofs. Um, it's proof of theorems of the form there is an x such that p of x is true, um, and hence the name. So we find an explicit value of c for which p of c is true. Uh, just to remind you very quickly, what we saw so far are the direct proof, the proof by contrapositive, and the proof by contradiction. And we learned them for any property of the form for every x p of x, or properties of the form for every x p of x implies q of x, particularly. So we had several examples in coming from the odd even properties on integers, and with one example also tackling rational and irrational problem numbers. So when it comes to properties of this form, there is an x such that p of x is true. Um, what's called constructive existence proof, well, it's sufficient to find one particular value, one explicit value for which the property holds, and hence you can generalize it using existential generalization to this form, this desired form. Example, if you want to prove this property, you want to show that there is a positive integer that can be written as the sum of cubes of positive integers in two different ways. Well, you have to find that integer, okay? And I think nowadays, when you have computers and you can write software that automatically run on it, you can implement an algorithm that would find for you eventually by trial and error. It means exhaustive search, or you can also make certain optimizations, or use what we call heuristics to efficiently and quickly find such elements. So in fact, back in the 19th century, a work done by those mathematicians, you can read the details in the book, they found out a number for which this property holds, okay? Clearly, since this number is too small, I think relatively small, I think you can write a naive algorithm and you can eventually find it. Um, two things to be said about constructive existence proofs in general is that sometime when you have a certain uh, exotic property that hasn't been exhaustively studied in the literature, and that you can think of. Well, you can run algorithm to find such values. Eventually, if you find several different values, let's say x0, x1, x2, etc., all of them satisfying the property of p of x, well, you can then study these particular values and check what's common in between them. And you can then try to generalize this into something like for every x in the domain of those xi's, when you have that particular property in common q of x, then necessarily p of x must be true. Okay. So this is one case. The other case, the other extreme, is when you don't find any x for which the property holds. Okay, and then you may start formulating a certain conjuncture, such as for every x, maybe not p of x is true. Okay, and then also from this observation, you can generalize this format or induce this format, and then you can try to create up a proof for it. Of course, the machine won't be able to help with it, okay? Um, or at least in the best case, it can partially help in improving this. And then the mathematician has to work manually to prove such properties. Um, Sometimes we are interested in showing actually um, that it's not possible to come up with um, or to show that there is a certain value that satisfies a certain property, we can prove its negation. We can show that it's not possible that um, uh, you can come up with a value that does not satisfy the property. Okay, well, this is equivalent to the fact that there must be a value for which the property holds. Okay, so we call this approach non-constructive existence proof. So in which we assume that no C exists, which makes P of C true, and then we derive a contradiction afterwards. Okay. Um, so if not uh, for every x not p of x, then clearly there must be an x such as p of x. Okay, and we call this proof by contradiction for existential properties, non-constructive existence proof. Example: if you want to show that there exists rational numbers x and y such that x to the power of y is rational, but you can prove this with non-constructive constructive existence proof by assuming that actually there does not exist any two irrational numbers x and y such that x to the power y is rational. For instance, you can use this to show that there is a contradiction um, by using the information that square root of 2 is irrational, proved earlier in the during the live sessions in prior in the last session. So now we can consider square root of 2 to the power square root of 2. Okay. Well, this is actually um, can be safely considered to be irrational. Okay, based on our assumption. Okay. So since x to the power y is equal to square root of 2 to the power square root of 2, if we take x and y to be equal to square root of 2, okay? So, and since x and y are irrational, then necessarily, according to our assumption, their power must also be irrational, okay? Um, Now we can use, in this case, x equal to square root of 2 to the power square root of 2, and y being equal to square root of 2 simply. Since both of them are irrational, then x to the power y, according to our assumption, must be irrational. However, if we unfold it, we find that this is equivalent to square root of 2 to the power square root of 2 times square root of 2, which is square root of 2 square, and which yields square root of 2 to the power of 2, which is equal to 2, and which is rational actually. So hence, um, our assumption cannot be true, and there must exist two irrational numbers, x and y, such that x to the power y is rational. Okay. Of course, once you do this elaborate proof, you can say, why wouldn't we get the idea to use this as an x and this as a y, okay? And then just do the calculation and show with a direct proof that this to the power of that, okay, if this is x and this is y, then clearly x to the power of y is equal to 2, which is rational. Yeah, of course, you could do this absolutely. Okay, it was just an example where we can where we were able to show you how to proceed technically and logically with a proof by contradiction for an existential theorem or an existential property, and how this would actually um, uh, be achieved um, rigorously. Okay, so the last, the last actually type of proofs is the counterexample uh, proof. Actually, it's typically a disapproval. with a certain theorem of the form for every x p of x. Okay, so when you want to disapprove this one, well, you can actually, to show that this is false. Okay, this is equivalent to show that there exists an element, one element at least, such that not p of x is true. Okay, so this is another use of the existential um, um, predicate formula. You show that at least one element does not respect the property. It means that the property cannot be true for all the elements. Example, if um, we want to refute the fact that every positive integer is the sum of the squares of three integers, okay, then we can try to show this with the number 7, for example. Of course, you could prove it with plenty of other numbers, but maybe this is one of the first or smallest numbers with which you can give a counter example, actually. Um, so clearly, 7 cannot be written as the sum of squares of three different integers. Okay. Um, one last word about this deck of slides about proofs is a remark, actually, to avoid um, um, steps that are done in a hassle and that do not actually um, uh, um, where we may commit pitfalls while uh, um, listing them or proceeding with them from one step to another. So example, if you want to prove that 1 equal to 2, one way is to do this proof, okay? Um, well, actually, you can start from the fact that um, um, if A is equal to B, then, and this can be done, actually can be satisfied by plenty of values, okay? Let's say A and minus A, let's say. Then in this case, A squared can be written as A times B, which means that A squared minus B squared is equal to A times B minus B squared. So we are just subtracting the same positive amount from both sides. Uh, the one to the left is can be rewritten as I minus B times A plus B, and the term to the right can be written as B times A minus B, which actually leads to A plus B being equal to B. And now 2B is equal to A, which means that 2B, since A is equal to B, so it means that 2B is equal to B. Okay, and uh, by dividing by B, we obtain 2 equal to 1. Okay, so at the first sight, this seems okay and convincing, and it leads to something very surprising. But if you check the details, I think you can already spot a dramatic pitfall here. Okay, so just pause the video and think about it. Okay, and I think you realize quickly that at step number 5, when you divided both sides by a minus b, okay, um, you didn't think about the first premise. Okay, so you can divide both sides by a minus b, but on condition that a minus b is different than 0, except that when a is equal to b, okay, uh, well, a minus b clearly is not equal to this. It's equal to 0, actually, okay, and it's not different than 0. So for this simple reason, you cannot proceed from step 5 and on, and this shows that this is a wrong proof. Okay, one of the steps were misleading. This happens sometimes while doing mathematical proofs, and it happens even in advanced research work. But this is why there are scientific committees that review the work of each other, and they refine study and detail the work of the others before publishing it officially. And sometimes, even if it's published, it can be retracted afterwards from the for those reasons. Actually, it could be simply a major pitfall that cannot be corrected, or it could also be a simple step that once corrected, it would yield a corrected proof at the end. Okay. So for you, actually, at this level, you just have to pay attention that even if you are driven by the final outcome that you would like to prove, don't go in a hassle and don't allow yourself to make non-sound steps at any moment, okay? Even if the property is proved already or seems intuitively correct, so just make sure that you are using all the time sound steps when you go from one steps to the next one, okay? So in summary, if direct methods of proofs do not work, we may need a clever use of proof by contraposition or by contradiction, or we can show that the theorem doesn't hold using a counterexample, okay? And sometimes when the theorem is about an existential property, a property that is to be proved that is true for at least one element, then it is sufficient to come with a particular element for which P of X is true. And we call this constructive proof. Another way of doing constructive, of using existential properties is when you want to refute a certain property. So you want to show that it's not the case that for every x, p of x, well, this is equivalent to showing with a non-constructive a proof that for some x, it's not the case that p of x holds. So it's kind of a proof by contradiction to the universal property. In the next uh, deck of slides, actually, we will jump to three additional methods. The proof by case, and then the proof without loss of generality, and that actually relates to the proof by case, and finally the backward reasoning method. And then we will be done with this part about proofs.